have ourselves a graph, okay? A little going down, a little going up, and we have some questions about said graph, so let's answer those questions. On which interval is the graph concave up? Concave up looks like this. So our concave up starts here, still concave up, 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 and this is right about where it changes. So what we'll say is negative infinity. Now that parentheses means you don't include it, and you wouldn't include negative infinity anyway. It's a concept. And it goes all the way to 0. Now we're not going to make a bracket. We're going to make a parentheses because at 0 is where it changes. And so the moment it changes, called an inflection point, is neither concave up nor concave down. So no brackets, okay? Just the parentheses, which means you don't include that number. Concave down looks like this. And that goes from 0 all the way to positive infinity. Don't include either of those numbers either. On what intervals is the graph increasing? Now, it's important to understand that graph increasing is not the same as rate of change increasing. That's concave up, concave down stuff. This is just asking, where is the graph going upwards? So this part of the graph is going downwards, and that's going to answer D, so we might as well get it out of the way. At B, it starts going upwards, increasing, and at D, it starts going downwards again. So to answer this question, we will say between B and D is where this is increasing. Now we're not going to include B and we're not going to include D because at B, it goes from decreasing to increasing, and at that very moment, it's a flat slope, which means it's neither increasing nor decreasing. On what intervals is the graph decreasing? Well, we already answered that. From negative infinity to B, and then increasing, and then from D to negative or positive infinity. Now we're not going to include things, but what we're going to do is, since there's two intervals, we say negative infinity to B, don't include it. This means union. That's when you have more than one interval. And then it's also decreasing from D to positive infinity. Okay? Find the zeros of the function. The zeros are where my line crosses the x-axis. Here at A, here at 0, and here at E. So we will say the zeros are when x is equal to A, when x is equal to 0, and when x is equal to E. And last but not least, find the y-intercept of the function. That's where my line crosses the y or f of x axis. And it looks like since it crosses the origin, the y-intercept is going to be 0. So why not be a little bit specific and say, well, 0, 0, the origin. Okay? Fun. Estimate the rate of change at x equals 1 for the function f of x equals negative 1/2 x squared plus 3x minus a half. Now, we know the average rate of change. The average rate of change, the AROC, is going to be f of b minus f of a over b minus a. This isn't asking for that. This is asking for the rate of change at the very moment when x is equal to 1. Well, this involves calculus, and we don't know calculus yet, so we're going to use our calculator to give us a trick. See, we don't know the exact rate of change at 1, but what we could do is we can allow an interval that's awfully close to 1, like how about 1 and 1.0001? See, that's not going to give us the actual exact rate of change at 1, but it's going to give us the average between 1 and 1.0001, which last time I checked, 1 and 1.0001 is awfully close to each other. So that's how we're going to handle this. So what I'm going to do is I'm going to run to my calculator. I'm going to find out f of 1.0001 minus f of 1 over 1.0001 minus 1. So let's take a step aside and do that. All right, so the way we're going to handle this is we're going to type in our function right into here. We're going to type out negative 1/2, so negative 1 divided by 2. You could do 0.5 if you want. Really, it makes no difference. Negative 1/2 x squared plus 3x minus 1/2. So I'll do 0.5 because, fractions make me nervous. When I take a look at the graph, I'm trying to find the instantaneous rate of change at 1, which means, whatever my slope is at 1 is going to be my guy. And it looks like it could be a +1, +2, +3, but I'm not so sure. So what I did is I set up 1.0001 and 1. So I need to find both of those. So second calc is going to let me find a value at a specific thing. I'm going to use this to find the value of 1.0001 by hitting enter and then typing out 1.0001. Hit enter on that, and that gives me 2.0002. Okay. Now, if you remember from the problem, we said that we're going to do f of 1.0001, which is that, minus f of 1. So what's an easy way of finding out what f of 1 is? Go to second table, and there's f of 1. It's 2. So the equation that I'm going to set up is that f of 1.0001, so let's go back here and set that up, which was 2.0002 minus f of 1, which is 2, all of which divided by 1.0001, so let's throw that into parentheses, 1.0001 minus 1, close parentheses on that, and we get 2. So again, if we were to look at this graph, we can kind of see that at 1, if I were to draw a line there, it might have a slope of 2. Maybe. I don't know. Use your imagination. But that's what we're going to get to dunzo. All right. So after all of that, we ended up getting what? 2.0001. We ended up getting 2 here. Oh, actually, that was 2.0002, wasn't it? I'm trying to remember what I got. 1.0001 minus 1. When you did the math, you got 2. And so we said 2. And again, I wasn't really able to draw anything on the calculator, but what we saw was a picture that looks like that, a perfect parabola with a bump over here. And so at 1, which we could say that's 1, we had some type of slope, and that slope kind of looked like 2. So that slope is going to be 2. And the rate of change is a fancy word for slope, because doesn't that just look like the slope formula? It does. It should, because it is. The values of a function g are given at selected x values in the table below. The function is either concave up or concave down, but not both. Determine if the function is concave up or concave down. Well, something is concave up if the rate of change is increasing for concave up and decreasing for concave down. So what do? Well, let's find the rate of change. The way you find the rate of change is you go to your table. You make sure that the x values are going up by the same number, which they are. These are called equal length input value intervals. And then you see what's going on here. Okay, so to get from 18 to 20, we add 2. To get from 20 to 20, you add 0. To get from 20 to 18, you subtract 2. And to get from 18 to 14, you subtract 4. Now, whenever we do this, you are finding the rate of change. Because what you're doing is you're finding how g is changing over the course of one step. And you add 2, subtract nothing, subtract 2, subtract 4. The rate of change goes from 2 to 0 to -2 to -4. Those numbers are decreasing, which means this graph is concave down. Now, if you wanted to, you could probably draw your own picture of this and graph these plots and see that you're going to get something that looks like this. But that's no fun. This is the best way to do it because, it's all precalculus-y. Ooh, look at this weird-looking unnatural picture. Find the absolute minimum, find the absolute maximum, find the relative minimum and the relative maximum. So the absolute minimum is the smallest point on the graph, which happens to be here. So it looks to me that the absolute minimum is going to occur at the point -6, -2, which means my absolute minimum value is -2, and that happens at the x value of -6. Okay, my absolute maximum doesn't exist because this guy is going to keep going on forever. So there is no absolute maximum. It goes on forever and ever and ever and ever and ever. Now, a relative minimum exists at any point where you basically bottom out anywhere, whether it looks like that, or at this case, could look like that. So that is a relative minimum. So we have several here. We have a relative minimum here, because that's where it bottoms out. Then it goes up, comes back down, bottoms out right there. Goes up, comes back down, bottoms out right there. So we have 3 relative minimums at -6, -3, and +2. My relative maximums are where things go up and peak out, or hit like this. So that happens, it looks like 2 spots, right here, right here. You're not going to include there because that's going on forever, and at no point will it get like the maximum. It's going to keep going. So -4 is going to be a relative max, and +1 is going to be a relative max. And there you have it. Find the degree of the polynomial from the given input and output values. All right, so when you're given a set or a table of points, the way you find if something's linear or quadratic is you look for the rate of change, or look for the rate of change of the rate of change, or keep going if you have to. All right, so the way you look for the rate of change is you first make sure that your input values are going up by the same number, and they are. That's called equal length input value intervals. You are making sure that these go up by the same number, they go up by 1, we're in good shape. Now, to test to see if something is linear, you are seeing if this rate of change is the same number throughout. So you figure out what number you add or subtract to get from one number to the next. And if they're all the same, that means the average rate of change is the same and it's linear. You add 1, you add 3, you add 5, you add 7, you add 9, you add 11, you add 13. Is this guy linear? No. So the second time is to test if it's quadratic, and you do it again. You see what you add for every single one to figure out if the average rate of change of the rates of change are the same. And if that's the case, like it looks like it is, 1 to 3 is 2, and 3 to 5 is 2, and 5 to 7, and 7 to 9, and 9 to 11, never forget, and 11 to 13, they're all 2. So my guy, since the rate of change of the rate of change is the same, is quadratic. So find the degree of the polynomial. The degree is 2 because it's a quadratic, baby. Describe the end behavior in limit notation. I have myself a polynomial graphed, and what it looks like is happening is this graph going to the left is moving downward, and going to the right is also moving downward. Another way of saying going to the left is the limit as x approaches -infinity. That means x is heading towards -infinity, moving to the left. My graph, as I move to the left, is going downward, which means it's heading towards -infinity. So the limit as my picture moves to the left is going down to -infinity. That's one side of the end behavior. The other side of the end behavior is if I move to the right. When x gets larger, we say the limit as x approaches +infinity. And in this case, as x approaches +infinity, it's also going downward. So as x approaches +infinity, we are also heading towards -infinity. What you're allowed to do, you're allowed to go in the same exact spot both times, that's fine. But this is how you would describe this polynomial in limit notation if we care about its end behavior. All right, looks like we have ourselves a gross-looking rational function type thing, and we are being asked to find the end behavior, ask if there's a horizontal asymptote, and so write out the equation of the horizontal asymptote. Now, it looks to me that we do have a horizontal asymptote, and we do have end behavior, and things seem to level out at this number right here. Okay, things seem to level out right there. This guy flattens out here. This guy starts down here, comes back up, and starts to flatten out right there. Well, what number is that? That seems to be 4. So what we're going to say is the end behavior of this guy, as x moves to the left, we are approaching 4. Will we ever hit 4 again? Probably not. But as we move to the left, as x approaches negative infinity, we are heading towards 4. As this guy moves to the right, it looks like we're also approaching and probably never hitting 4 as well. Is there a horizontal asymptote? If so, write the equation of the horizontal asymptote. Well, if you're going to level out at a specific number, which I am, that horizontal asymptote is going to be a horizontal line. Horizontal lines are in the form y equals a number, and since that number where things seem to level out is 4, is going to be y equals 4. So is there a horizontal asymptote? Yeah, and here it is. Fun stuff. All right, so we have h of x. It's all, multiplied out and everything, and it's asking questions about domain, whole, zero, vertical asymptotes, horizontal asymptotes, y-intercept. So what we need to do is we need to view this in its factored form along with its regular standard form. So the factored form is going to be that is difference of squares, x plus 3, x minus 3. The denominator is two numbers that add up to -2, would multiply out to -3. So x minus 3, x plus 1. Now we see what's going to happen here. We see that we have an x minus 3 and an x minus 3. We'll deal with that when we have to, but not quite yet. The domain is any number that takes the denominator and makes it equal 0. Now the two denominators, and what I'm going to do is I'm going to look at each factor and I'm going to look at every number that makes it 0. My magic number for you is -3. My magic number for you is regular 3. My magic number for you is regular 3. My magic number for you is -1. Now, the domain is any number that makes the denominator equal to 0, and the numbers that do that are going to be 3 and -1. And if you're thinking, well, what about these? Aren't these going to cross out? Yeah, kind of, but the original problem looks like this now. And so we have to take into consideration the original problem before we cross anything out. So I'm not allowed to plug in -1, and I'm not allowed to plug in 3. So the domain is going to be everything up until -1, -1 to 3, union, and 3 on to infinity. That's my domain. My wholes are going to be any number whose factor is seen both in the numerator and in the denominator the same amount of times. X minus 3 appears in the denominator, x minus 3 appears in the numerator, which makes 3 a whole. So x equals 3 is a whole. My zeros are any number in the numerator that equals 0 that is not a whole. So 3 is not a whole because I'm not allowed to plug in 3 in the first place. I'm sorry, 3 is not a 0. 3 is a whole. 3 is not a 0 because I'm not allowed to plug in 3 in the first place. So 0 is -3, and that is it. My vertical asymptotes are any number that is seen in the denominator that is also not a whole. -1 is the only vertical asymptote, and since -1 is a vertical asymptote, we write out x equals -1. The horizontal asymptote is where everything levels out. Okay, in other words, my end behavior. You find your end behavior by taking the leading term divided by the leading term and plugging in infinity. X squared over x squared equals 1. Plugging in infinity into 1 changes nothing. So my horizontal asymptote is the horizontal line y equals +1 because everything levels out at +1. My y-intercept is what happens when x is equal to 0. Well, when x is equal to 0, you go away, you go away, you go away, and you're left with just the constant divided by the constant. So -9 divided by -3 is +3. So there you have it. You're given a regular old rational function, domain, wholes, zeros, vertical asymptotes, horizontal asymptotes, y-intercept. Hope this helps. All right, we have ourselves a rational function, and we are being asked to answer a bunch of questions about it. Now, let's take a look at what we have first. We see in the denominator multiplicity. This is what's called a perfect square trinomial, and we have multiplicity. When you're dealing with multiplicity and you're expecting things to be the same, that kind of changes domain, not so much domain, but whole, zeros, and vertical asymptote behavior. So let's do this first. Let's ignore the multiplicity part. We'll get to that in a second. Let's deal with the domain. The domain is what number am I not allowed to plug in? Any number or numbers that makes the denominator equal to 0, I'm not allowed to plug in. For example, 2 would make the bottom equal to 0. 2 is the only number that would make the bottom equal to 0, which means 2 is not allowed in my domain. So the way we write that out is we say negative infinity to 2, not include the 2, that's what the parentheses means, union, and then 2 on to infinity. Now I have to take into account this multiplicity thing. What I need to do is I need to factor the top part, the numerator. So I need to come up with two numbers that add up to 4 and multiply out to negative 12. And I think x plus 6 and x minus 2 should do it. Now I still have x minus 2 squared on the bottom. I'm going to write this out both ways. Not that it's necessary, but it might help me understand things a little bit better. X plus 6, x minus 2, x minus 2, x minus 2. Now, whenever you have multiplicity and you have repetition going on in the numerator and the denominator, this is what you're going to take into account. Okay, my magic number here is 2, my magic number here is 2, and my magic number here is negative 6. Whenever your multiplicity, and if you have repetition, whenever your multiplicity on the bottom in the denominator is an odd number more than whatever repeated factors you see up here, you are going to have a vertical asymptote. Okay, so basically the behavior of this happens. Now I know that's a whole, but this 2 is also the same exact number. So which is it? Is it a whole or is it a vertical asymptote? Well, since this goes away, the graph now behaves like this. Either way, you're not allowed to plug in 2. But now, since this part goes away, you are left with a vertical asymptote, and the whole behavior is now gone. So 2 is a vertical asymptote and not a whole. That leaves me with a negative 6 up here that I am allowed to plug in, and that negative 6 becomes a 0. So if you're wondering, all right, well then what's my whole? There is none. And again, that's because you have more factors on the bottom than you have up here that are the same thing. So that takes me to my limit notation and horizontal asymptote and then behavior and all that stuff, which is basically the same thing. Except for this part, limit notation of the vertical asymptote. Now, since the graph behaves like this, my picture is either going to look like this guy or like this guy, because now it behaves like this. And if I wonder, all right, well, which one is it going to look like? It's going to look like U, this one right here. And the reason why it looks like that right there is because both of my leading terms are positive. So it's going to take on this behavior. If I wanted to go into more detail, I can make myself a sign chart, but I'm not going to do that. So what it's asking me here is the limit notation of my vertical asymptote, which happens at 2, is going to look like this. As I approach 2 from the left side, that's what that little minus sign means, of what is it, h of x? I am going downward. So my limit as I approach 2 from the left has me going down here, which means negative infinity. Okay, let me scooch this out of the way because I don't need it anymore. My limit as I approach 2 from the right side, which means I'm coming this way, is going to be positive infinity. So h of x equals positive infinity. Horizontal asymptote is asking where this levels out. Well, in order for me to find out what my horizontal asymptote, where it levels out, I need to do the end behavior at the same exact time. So the way you do the horizontal asymptote, the end behavior, stuff like that, is you take a look at the leading term in the denominator and the numerator. So the leading term in the numerator is x squared. The leading term in the denominator isn't as obvious, but it's an easy fix. If I were to do x times x, or x times x, or x times x, I also get x squared. X squared over x squared simplifies out to regular 1. So my horizontal asymptote flattens out at regular 1, which is going to be the equation y equals 1. Which means my end behavior, as I move to the left, is going to flatten out at 1, and as I move to the right is also going to flatten out at 1. So the limit as x approaches negative infinity, as x decreases without bound, of h of x is going to be the same as the limit as x approaches positive infinity, and those both equal 1. Since I ran out of space there, I wrote it out as they all equal each other. But yeah, there you go. Kind of a complicated problem. Multiplicity never makes things fun, but we figured it out and we had a great time. Hope this helps. All right, I'm given a graph here and I'm being asked to find the limit notation of the holes. Now, the hole exists where you have on your graph a little hole right there, which is a circle. Now, the limit notation of a hole means as I move from the left and from the right towards that hole, where am I going? The hole exists when x equals 5. So coming from the left side, here in red, I would write this out as the limit as x approaches 5 from the left. That little negative on the top right means I'm moving from the left. When I move from the left, if I were to plug in 5, I would get something that doesn't exist, that's undefined. That's what a hole means. But as I approach 5 from the left, I seem to be heading towards that number 4 right there. So the limit as x approaches 5 from the left has me going towards the y value of 4. Now, coming from the right side is a lot of the same. If I head towards 5, which is my hole, I would write that out as the limit as x approaches 5 from the right side, which means a little plus sign right there. As I approach the x value of 5 from the right side, I hit the same exact y value of 4. So the answer is going to be exactly the same from the left and from the right. And that's how you do limit notation of a hole. Oh yeah, the binomial theorem, one of the worst things in AP Precalculus. You got to learn it though, because chances are you'll see like one random problem on the AP test that asks you to do something like this. So this is a two-step process. Step number 1 is you need to draw out what's called Pascal's triangle and go to as many levels as this tells you to do. Okay, now the first level of Pascal's triangle is in number 1. Okay, and technically, even though I called it the first level, this has to do if your degree is 0. The second level is going to be 1 and 1, and that has to do when your degree is 1. Okay, now the way you work with Pascal's triangle is don't memorize anything after this. Okay, whatever numbers at the end are always going to be 1, and whatever numbers in between are always going to be the sum of these guys here. So 1 plus 1 is 2. Okay, drop down the 1. 1 plus 2 is 3. 2 plus 1 is 3. Drop down a 1. Drop down a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Drop down a 1. Now I'm done because this is degree 2, this is degree 3, and this is degree 4, which is what I want. Now, this gives me the coefficients for when I multiply this out. This does not give me any answer. This just helps me figure it out. Now, the rule says if I have something like a plus b to the 4th, I use these numbers and I do 1a to the 4th plus 4, and then you work your way down with the a's and work your way up with the b's. So a to the 3rd, b to the 1st, plus 6. A squared, b squared, plus 4. A to the 1st, b to the 3rd, plus 1, b to the 4th. Now that looks pretty sloppy, but let me do it again with these actual values here that I'm supposed to use. U would be my A and U would be my B. So the way that I actually set it up is I say 1 times 3x to the fourth plus 4 times 3x cubed times b, which is negative 2 to the invisible first, plus 6 times a squared, which is 3x squared, times negative 2 squared, because it's b squared, plus 4 times a, which is 3x to the invisible first, times b, which is negative 2 to the fourth. I just ran out of room. Plus 1 b to the fourth, which is negative 2 to the fourth. And then you simplify that guy, which I don't need near as much space for. 3 times 3 times 3 times 3 is 81, and 81 times 1 is 81, so 81x to the fourth, plus 3 times 3 times 3 is 27, 27 times 4 is 108, 108 times negative 2 is negative 216, so let me get rid of that plus sign and make it minus 216, x to the third, plus 3 times 3 is 9, times 6 is 52, 52 times, 54, sorry. 3 times 3 is 9, 9 times 6 is 54. Negative 2 squared is 4, and 54 is 218, 16. 216 x squared. That's supposed to be negative 2 to the third, so if I miswrote that, let me fix that right here. Negative 2 times negative 2 times negative 2 is negative 8. Negative 8 times 12 is negative 96. So negative 96 regular x. And then negative 2 times negative 2 times negative 2 times negative 2 is just 16. So again, very easy to make little calculation errors like I did over here. Very easy to expect that you have enough space and you don't, like I thought I did. But that's how you do it. Not pretty, not easy. You'll probably have to do one on the AP exam, so I hope this helps. Given the table of values for f, blah, 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 let g of x equals f of x plus 2, and then find g of 2. All right, so if g of x equals stuff, then g of 2 means replace every x with 2. So f of 2 plus 2. What's f of 2? Oh yeah, up here. When x is 2, f of 2 is 10. So f of 2 is 10. So let me replace f of 2 with 10. And 10 plus 2, let me get out my calculator, is 12. So g of 2 is 12. Select the appropriate model for the data. Is it linear? Is it quadratic? Is it cubic? This is what you're looking for. In order to find out from a table if something is linear, quadratic, or cubic, you need to find the rate of change as long as these guys go up by the same number. That's called equal length input value intervals. So if something's going to be linear, that means to get from 4 to 15 and from 15 to 50 and from 15 to 121, these have to be the same number. Well, to get from 4 to 15, you add 11. To get from 50 to 50, you add 35, which means right off the bat, it's not linear. This one has you adding 71. This one has you adding 119. And this one has you adding 179. So is it linear? Nar. Nar, as my friends from down under would say. Let's try it again. If it's quadratic, then the rate of change of the rates of change are going to be the same. So how do we get from 11 to 35? Add 24, of course. And from 35 to 71, add 36, of course. So it's not going to be quadratic because these numbers are different. So you add 48, you add 60. So it's not quadratic. So in order for something to be cubic, the rate of change of the rate of change of the rate of change has to be the same over equal length input value intervals. So how do I get from 24 to 36? Add 12. How do I get from 36 to 48? Add 12. How do I get from 48 to 60? Add 12. Is it cubic? Yep. So this is cubic because the rate of change of the rate of change of the rate of change are the same over equal length input value intervals. Isn't that fun? The data shows the salary in thousands of dollars for employees given their year's experience. So we have this information right here, and it looks like it's a calculator problem. So what we're going to do is let's throw all of this stuff into a calculator. All right, after we're done throwing it into a calculator, we'll answer these three questions. And it's asking us to use regression. So rather than doing the whole, like, let's see if this adds up and do that thing, let's let our calculator do the job, because I have a feeling it's not going to be absolutely perfect. So let's just plug it in to our calculator and see what our calculator gives us. All right, so let's type some of these numbers in. Stat, edit. Now, I think that what I said before is, rather than like counting, if you're already noticing already, I really can't do the, hey, let's count and see how far apart these guys are, because these numbers are not equal length input value intervals. So forget what I said back there like 30 seconds ago. 2, 4, 5, 8, 9, 12, 15, and then we got 48, 54, 58, 68, 73, 80, 88. All right, no mistakes at all. First thing that I have to do is figure out if this is linear, quadratic, or cubic. So why don't I graph these points on the graph? Now, hitting graph won't do anything for me. What I have to do is I have to hit second, stat plot. I have to turn the stat plot on. And already what it's going to do is it's going to give me the dots according to the stuff that I plugged in. Before I hit graph, since I'm using stat, I need to go to zoom first and do zoom stat. So go to 9 and we'll see our dots. Now those dots aren't in perfect order, but you know what? They look pretty linear to me. So we're going to go with linear for that one and write that down. All right, so basically the dots were in a nice straight line, not perfect, but good enough. So I'm going to circle linear for that one. Now that I know that it's linear, when it asks me to write an equation of the regression curve, I'm going to use linreg and see what equation I get in my calculator. Now part B is asking us to find the equation of the regression curve. We know that this is linear. So let's quit out of this. Our points are still in the thing. Let's go to stat, calc, and use linreg. Use 4. So when I go to 4, and since, by the way, C is asking me to use this equation to plug in 11, what I'm going to do is when I go to store regression equation, I'm going to hit vars, y vars, function, y sub 1. And what this will do is this will store whatever equation that I get into y equals, so I can do part C without having to type out the whole world. So if I hit enter, it gives me my equation. And so when I round it to 3 decimal places, it's going to be y equals 3.137x plus 42.349 end. Mr. Calculator says that the equation is y equals 3.137x plus 42.349. That's my equation. Use that equation to predict the salary of an employee with 11 years experience. So I'm going to throw that back into my calculator and see what I get. Now, since we stored that equation into y equals, if I want to find out what happens at 11, all I have to do is hit second table, go down to 11, and see what number I get. And that number I get appears to be 76.8603, blah, 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 blah. So when I write that out, I have to remember this is in thousands, so I'll make sure I account for that. But that's how I do this problem on my calculator. Easy peasy. Now at 11, my calculator gave me something like 76 point blah, 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 blah. But this has to do with 76,000 blah, 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 blah. So the number in my calculator was 76.86036,036. That translates to $76,000. $860.36. Baby, that is a nice bit of coin. In an experiment, the number of mold spores can be modeled using a geometric sequence. Very interesting. Where the first day of the experiment is day 1. If the population on day 6 of the experiment is 6,000 and the population is 20,000 on day 10, find the mold spore population on day 8. So what we're going to do, since this is a calculator problem, is we're going to use exponential regression. And once we find exponential regression, we should be able to take that equation and plug in 8 to find our total population. So let's step to the side and do that. All right, so for this guy, we are going to do exponential regression. Start out by hitting Stat, go to Edit, and we're going to type in the 2 data points that we have, 6 and 6,000. So let's do 6, move to the right, 6,000. And then we're going to do day 10. So they typed it out, worded it out, whatever you want to say, backwards. So just be careful. We're doing exponential regression. And I'm going to use this equation to plug in 8. So what I'm going to do is I'm going to hit Stat. I'm going to go down to 0, which I believe is exponential regression. There it is. But I want to use this equation again. So this is what I'm going to do. I don't really care what the equation is. I just want to use it. So as I hit enter, wherever it stores regression equation, that's what that means. We're going to go to vars. We're going to go to y vars function y sub 1. Now, yeah, this gives us our equation, but look how gross it is. Wouldn't it be nice if we could just take that and somehow plug in 8? Well, we can because there it is. By doing that vars thing, it plugs in our equation right there. And in order to find 8, maybe we could just go to our table by hitting second graph and going down to 8 and finding out that there's our number right there. So the answer is B in this case. All right, so since I got the number 10954 point blah, 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 let's round that down to 10954, and then B is going to be our answer. So exponential regression, geometric sequence, same thing on a calculator. The table above gives values of an arithmetic sequence. Which of the following is an equation of a linear function that could represent the sequence? So what we have going on here is we have point slope form. So if you remember from back in the day, point slope form looked like this. Y minus y sub 1 equals m times the quantity x minus x sub 1. But this is a slight manipulation. So what I'm going to do is I'm going to use this information. I'll call you x sub 1. I'll call you y sub 1, right? That way I can plug stuff in. And is that looks like they want me to use 3 and 6? Yeah, maybe. I don't know. We'll find out. And what I also need to do is I need to find my slope. So the slope can be found by doing something like 8 minus 6. This is the slope formula. 6 minus 3. This is the slope formula. 2/3. This is the slope formula. And then when I plug stuff in, I get y minus y sub 1, which is 6, equals 2/3 times the quantity x minus x sub 1, which I called 3. So I need a slope of 2/3. So not you, yes you, not you, yes you. And I take it back. They actually don't want me to use 3 and 6. They want me to use 6 and 8. So why don't I change this? Why don't I make you my x sub 1 and you my y sub 1? So now I have, watch me. I'll turn you into an 8. I'll turn you into a 6. But when I add 8 to both sides, it now will look like this. Y equals 8 plus 2/3 times the quantity x minus 6, which is going to be B. So kind of weird. The process that I used to do it wasn't, as exact as I wish it would be, but, that's what you do when you steal problems from the internet. The table shows values from an exponential function in the form y equals a b to the x, where a and b are positive constants. Which statement best describes the exponential function? So without doing too much, let's analyze what y equals a b to the x means. A is always going to be your starting point, your initial value, and b is going to be your common ratio, which you multiply every single time to get from one number to the next. In this case, my initial value is going to be 0.6. Okay, so I'm starting out with 0.60. It looks like every single time to get from one number to the next, I'm going to be very careful. I don't just divide by a quarter. I divide by a quarter over an interval of 2, but I don't think that's going to be necessary. I mean, what we definitely have is we have decay. So what's going to happen here is B is going to be some type of decay where we divide by 4 every 2, which means I guess I could legitimately say that I divide by 2. So if I were to force like a 1 in there and put a 0.30, that would work. So what I have is I'm dividing by 2 every time. So you're a half. So that's the equation I came up with. Is that what it wants me to do here? No, it just wants me to answer some logical questions. The function demonstrates exponential growth. No. The function demonstrates exponential growth. No. The function demonstrates exponential decay because A is in between 0 and 1. Well, that's not why. That just happens to be the case here, but that's not why it's exponential decay. It's exponential decay because B, my common ratio, is between 0 and 1. So it's easy to select C based off of the numbers that I got, but C is not why it's exponential decay. D is why it's exponential decay. DK Donkey Kong. The function f is given by f of x equals 16 times 49 to the x, which of the following is an equivalent form of f of x. So let me write it out. F of x, 16 times 49 to the x. Now I have a 16, which I know is 4 squared. I have a 49, which I know is 7 squared. 16 is also 2 to the whatever, but let's see what they want me to do. They want me to change 16 to 4 or keep it at 16. Well, 16 is 4 squared, so neither of you. So let's change 49 to 7 squared, and let's see what happens. So 49 is 7 squared to the x. When you have an exponent to an exponent, you multiply the exponents. So this can be written as 16, 7 to the 2x, which is D. F of x is an exponential function in the form f of x equals a times b to the x plus c. Select values of f of x are shown in the table below. A is 400. Okay. So A is 400, so let's write that out. F of x equals A times B to the x. A is 400, so let me quick change that. I wasn't thinking. 400 B to the x plus C, which is, I don't know. What I do know is if I plug in 0, that's going to make this part go away and become 1. So what I can do is I need to find C. I need to find whatever C makes this work. So what I'm going to do is I'm going to let x equal 0. And I know when I plug in 0, I get 373. So 373 is going to equal 400 times b to the 0th power, which is 1. If I subtract 400, that gives me C is negative 27. So that gives me an equation of y equals, or f of x equals 400 b to the x, which is what I need to find, minus 27. So what I'm going to do is I'm going to take all of these b values, plug it into my calculator, and test out 400 times 1.25 to the x minus 27 and see if that guy matches up. And if it doesn't, then I'll plug u in for b and try it out. Then I'll plug u in and try it out. Then I'll plug u in and try it out. So let's try a and see what happens. So let's test out a to make sure that a works. The equation that I'm going to use for a is going to be that 400 that I was originally given. A gave me 1.25 as my b, so parentheses 1.25, close it, to the x, and make sure you move to the right and not put it in your parentheses or exponent area. Subtract out 27. Now, in order for this to work, I really want to look at my table of values for 0, 1, 2, and 3. So let's go to second graph, and 0 matches up, and so does 1, and so does 2, and so does 3. Look at that. The answer is A. It worked. Hooray! A is my answer. Oh, how nice. A taco making company has a fixed overhead cost of 50 grand. Ooh, for rent, insurance, and other expenses. It costs an average of 26 cents to produce each taco, assuming these are the company's only costs, which is definitely not true. Write a model to represent what the company spends to produce X amount of tacos. All right, well, if you have $50,000, okay, and that's you want costs, C is cost. Okay, you're going to start out with $50,000. However, you gain, it also costs 26 cents to produce each taco. So plus 26 cents per taco. Did I call that a letter X? X tacos. And is that all I have to do? Yeah. Strange problem. It's almost too easy, but that's what it is. It's basically asking for what's the cost if everything is going to cost $50,000, period, and then 26 cents per taco. That's how much you're going to spend per taco. So that's it. Don't overthink it. I kind of did, but don't overthink that one. That one's a lot easier than it looks. Ooh, let f of x equals 8 over x minus 2 and g of x equals 4 over x minus 4. Identify the domain of f of g of x. All right, so what f of g of x looks like is you take f, you write it out like so, but anytime you see an x, you replace it with g. So it's going to look like this. Every time you see an x, you replace it with g minus 2. Now, this tells me right now, x minus 4 in the denominator, 4 can't have it. 4 is not going to be allowed in my domain, so that's part of my answer. Moving on. I'm not done yet because I have a fraction underneath a fraction bar, and it's just I got to combine fractions, so I'm going to do that. I'm going to multiply this guy by x minus 4 over x minus 4, distribute u, and that gives me 4 over x minus 4. By the way, 8 is still on top. I don't know why I forgot to write that out. 8 is still on top. Distribute that, you get negative 2x plus 8 over x minus 4. Now, since I distributed the negative 2, you're adding here. Now that I have the same denominator downstairs, I can combine the numerator, so 8 still lives upstairs. Okay, 4 minus 2x plus 8 is 12 minus 2x over x minus 4. Now, I'm going to quick move this 8 up here and put it over 1 so I can visualize a fraction over a fraction. Whenever you have a fraction divided by a fraction, multiply the top by the reciprocal of the bottom. So I'm going to multiply this by x minus 4 over 12 minus 2x over x minus 4 over 12 minus 2x. What that does, all of this cancels out and leaves me with 8 times x, 8 times negative 4, not that that really matters, 12 minus 2x. Now I have a brand new denominator. And according to this brand new denominator, if I set u equal to 0, add 2x, divide by 2, now x isn't allowed to equal 6 either. So my domain is everything but 4 and 6, which could be written out as negative infinity to 4, union, 4 to 6, union, 6 to infinity, which is u. Yeah, not very pleasant of a problem, but boy, was it so much fun. The figure above shows the graph of the function f on the domain between 0 to 9. There it is. If the inverse of f looks like that, what is the value of f inverse of 4 minus f inverse of 2? Well, here's the thing. If I say like f of x equals a number, okay, like for example, x and y like if I were to look at this and say, all right, well, 0 appears to match up with 0, and 2 appears to be 1, and what do I care about? What else do I care about? 4 appears to be 2, and that other 4 is probably going to show up. So let me see. 6 appears to be 4. The inverse would be if I were to completely flip these guys around. Completely flip them around. All right, so 0 is still 0, but 1 is now 2, and 2 is now 4, and 4 is now 6. Now, why did I use those exact numbers? Why did I see to it that I had 2 and 4 over here? Because now I have 2 and 4 on the left. So what I do now that I flipped everything, now that I found out, and basically that's how you approach this problem. You're saying, oh, if I want the inverse, then what I want to do is swap the x and the y values. So on this picture, I care about when y is 4 and when y is 2, and then swap them. So now I have them swapped. And so when I want to do this, f inverse of 4 is 6. Write that down here. F inverse of 2 is 4. And 6 minus 4 is this little tiny 2 right there. I've heard of Tiny Tim, but Tiny 2? Now that's a Christmas story that I'd want to watch. I hope that problem made sense. Given that b is greater than 0 and b is not 1, okay, write the equation below in its equivalent logarithmic form. All right, well, an equation in its equivalent logarithmic form has you take something in the form b of x equals y and changes it to log base b of y equals x. So this looks like this, and I need to make it look like that. So my x is 4, my y is 8, and my b is b. Makes sense? So I'm going to change this into log base b is base b of y is now 8 equals x, which is now 4. And you're my guy. Which equation matches the graph shown above? I'm going to do this in a very unique way. First things first, though, I know that this is a log because logs look like that. So adios and adios. Now, the way I can figure out which one C and D is you can do some memorization, but I'm going to go about this in a very unique way. I have like a base of 3, I have a base of 2, and I want to see which is which by comparing this to its inverse counterpart. Okay, so its inverse means if I were to graph it, you just flip the x and the y values. So this right here is the point 1, 0. Let's graph the point 0, 1. This is the point 2, 3. Let's graph the point 3, 2. This is the point 4, 6. Let's graph the point 6, 4. And this is the point that looks like 8, 9. So let's graph 9, 8. I'm going to try to attempt to draw this the best that I can. Usually I'm awful at this, but if I do like the little, sketchy way, actually didn't turn out half bad at all. Now, this is what I'm looking at. When I want to write this out as an exponential function in the form y equals a times b to the x, what I have is I start out with an initial value of 1. So that a, kind of useless, don't need it, let's get rid of it. Now what's really important is b tells you what you multiply every time. Okay, I go up 1, and then I go up 1, 2, and then I go up 1, 2, 3, 4. b acts as a common ratio. So what I get here is my base, whatever that is going to be 2. Because I multiplied, I went up 1, and I went up 2, and then I went up to 4. And so my base is 2, which means if I compare it back to the original version, D is going to be my answer. And you might be thinking, well, then what's that 3 stand for, sir? Well, notice up here, in the inverse, I went up 1 over 1, 2, 3. I went up 2 over 1, 2, 3. I went up 4 over 1, 2, 3. So when I erase this and go back to the original problem, When I was in exponential form, that base told you how many spaces I go up every time. Well, now it tells me how I go over every time. So when the base is 2, I go right 1, and then I go right 2, and then I go right 1, 2, 3, 4, and then the next one would be right 1, 2, 3, 4, 5, 6, 7, 8. And you might be thinking, all right, well, how much do you go up then? Well, notice this was right 1, up 1, 2, 3. Right 1, 2, up 1, 2, 3. Right 1, 2, 3, 4, up 1, 2, 3. So my next guy, if I needed another dot, I'd go right 8, up 3. Then right 16, up 3. Don't need to go that far. But what I learned by doing this is basically your number in front of log acts as almost like a rise for your slope. Okay. And then your 2, your base in this case, tells you how many times we're going to multiply to move over to the right next time. So I went over 1 times 2, right over 2, times 2, right over 4, then over 8, then over 16. Kind of interesting. I never looked at logs that way, but you learn something new every day with the math teacher. Go like and subscribe. When I teach logarithms, I'm always just like, have fun with it. Blink 182. But in this case, I am teaching logarithms, and you have to have fun with it because they're not a lot of fun. Maybe manipulating them, but the graphing aspect, I hate it. So this is what I do. Whenever I have to deal with graphing, domain, range, shifting, whatever, I always compare whatever log I have to this guy right here. F of x equals a log base b of x minus h plus k. Very kind of like a vertex form, but with logs. A gives you a vertical stretch or shrink. We're not going to see that here. I mean, we are going to see it, but it's not going to matter with what I'm being asked. Same thing with B, which gives you a horizontal stretch or shrink. Don't really care that much. Okay, this is what I care about. H tells me whether I move left or right. It's all backwardsy, but if I have something like x plus 3, I actually shift left 3. If I have x minus 3, I shift right 3. K is similar, but, normal, where if that's plus 3, I go up 3, and if it's minus 3, I go down 3. Now, why is all that important here? And what's really important is the fact that you are a positive number. If A is positive, a log is going to be graphed like this. Now, as you see, what happens on the left here is there's like a brick wall that this guy hits. All right, this is a vertical asymptote. That vertical asymptote says you're not allowed to plug in any numbers over here on this side. Why is that? Well, log, you're not allowed to take the log of a negative or a 0. So at some point, x or whatever this parentheses is has to be positive. So what that means is if I gave you a number with x, your domain would be h to infinity. Don't include h to infinity, okay? Because this is your brick wall and you're allowed to go all the way to the right. Similarly, your range is what you're allowed to get from the bottom to the top. Now you might be thinking, plus 2, that means you move up 2. That's going to change your range, right? Nope. No matter what, this guy is always going to continue going downward, no matter whether you shift it up 2 or down 2,000. It's always going to go down forever, and this guy is always going to go up and to the right. So your range, as long as you're a positive number, is always going to be negative infinity to positive infinity. So what do I have here? Well, since there's no number included with x in this case, I have an invisible 0, which tells me I have a vertical asymptote at x equals 0, or h happens to be 0. So my domain for this problem is 0, but not including 0. You're not allowed to plug in 0 because you're not allowed to take the log of a 0. It's against the rules. To infinity. My range is going to be negative infinity to infinity. So I did a little extra, a little more than necessary to kind of get to this point, which probably could have taken me about 30 seconds. I just struggle with the graphical side of logs, and if I do it and I'm a math teacher by trade, I'm sure there are people out there who kind of struggle too. So hopefully this helps. Like and subscribe. Let x and y be positive constants. Which of the following is equivalent to 5 log x plus 6 log y? We have two log rules going on. First things first, if you have a number in front of a log, you're allowed to take that number and make it the exponent of the stuff inside the log. In other words, 5 log x is the same as log of x to the fifth. What's my base? I don't know, 10. I don't have one. Plus 6 log y is now log of y to the sixth. There's another rule that says if you have the same base, and again, we're going to pretend that these 10s are there, even though they are 10s, we're just going to pretend that we can see them. If you add logs of the same base, multiply the insides. So what this becomes is, since we're adding log base 10 of x to the fifth and log base 10 of y to the sixth, I get log base 10 of x to the fifth, log to the sixth. Again, that 10 is not necessary. I just keep writing it down because it helps me visualize things a little bit better. I get b in this case. Pretty easy. Solve the equation log base 3 of x minus 8 equals 3 for x. Now, whenever I'm solving and I have x inside of a log or an ln, I want to write it out into its other form, but I'm going to be a little clever, be a little creative here. Okay, I'm just going to rewrite the equation. I want to get rid of that log base 3. How can I get rid of a log base 3? By taking 3 to the of both sides. Now, I know that's bad grammar, but that's how I remember it. Take 3 to the of both sides, and that allows these guys to cancel out, and you could drop down an x minus 8. 3 to the third is 27. Add 8 to both sides. Add 8 to both sides. X is going to equal 35. Now, before you just circle it and call it a day, make sure always, if you're solving a log, you're allowed to plug that number in. In other words, if I were to go up here and plug this number in and get log of a 0 or log of a negative, you can't do it. But I'm allowed to do this because log of 35 minus 8 is log of a positive number. This is allowed. That is our guy. Did I need you, Mr. Calculator? No, get out of here. Gregory and Spencer began a fitness routine in order to build their upper body strength. Gregory's gains in muscle mass can be modeled by the function g of x equals 50 times log base 2 of x, where x is greater than 1. Represents the number of days he has followed the routine, which means more than one day. Spencer's gains for the same period of time can be modeled by the function s of t, or x of x, equals 20 times log base 4 of x. After day 1, Gregory has gained more muscle mass than Spencer by a factor of what? So after day 1, I'm assuming means day 2. Dose. All right, so let's take a look at Greg. Let's take a look at g of x. Let's take a look at Gregory. Okay. If I want to find out what g of 2 is, there's not really much to think. Okay, you just say g of 2 is going to equal 50 times log base 2 of 2. Now, before you freak out and say, like, oh, how am I going to do that? I don't have a calculator. First off, log base 2 of 2 is 1. So he is 50 times 1, which is 50. So whatever that means, 50, I don't know, megatons, whatever. That's what Gregory is. Now, let's take a look at Spencer. Okay, let's take a look at Spencer, s of x. This is going to require a little bit more. In order for me to find s of 2, I have 20 log base 4 of 2. Now, I don't have a calculator. I can't do log base 4 of 2. But this is what I can do. I could use the fact that there exists a little guy called the change of base formula. Change of base formula says, actually, let me start it over here. If I have log base b of m, I can turn this into log base whatever I want. So log base t of m over log base t of b. Now, usually when we do this, we whip out our calculators and just do regular log and let our calculators do the work. I don't have a calculator. So in order for me to do log base 4 of 2, I'm going to be a little creative. I'm going to choose log base 2. So I'll do log base 2 of 2 up here, because that turns into 1, remember, over log base 2 of 4. And some of you might be thinking, I can't do that. I can't do log base 2 of 4. I can if I do 2 squared. You see, this becomes, 20 is still there, by the way. Log base 2 of 2 is 1. Log base 2 of 2 to the whatever power drops down the whatever power. So log base 4 of 2 just turns into a half. Interesting. 20 times a half is 10. So after day 2, Gregory is 50 whatever, Spencer is 10 whatever, and the question is how much more muscle mass by a factor of what? Well, 50 is 5 times more than 10. So that'll be our guy. Kind of a not fun problem, very difficult in my opinion, but yeah, we did it. The table gives values for a function f at selected values of m. Which of the following graphs could represent these data in a semi-log plot where the vertical axes are logarithmically scaled? That's a terrible word. All right, a semi-log plot basically takes a coordinate plane and makes it look different so that when you graph something that's logarithmic, you end up with a straight line. Okay, semi-log plots, basically what it looks like is the vertical part of it is you'll have a straight line, and then it gets smaller, and then it gets smaller, and then it's like really small like that. You guys are just regular old graphs. So let's get rid of you, and let's get rid of you. If you look closely and squint your eyes, you could see this process where you have all this space and then it gets closer and stuff like that. And the same thing happens for this one right here for D as well. Here's the situation though. The goal and the purpose of a semi-log plot is for you to demonstrate a logarithmic equation as a linear equation. So if I look at where these points are, C follows these points, okay? So like here would be 1, and then like, you know, that would be, I guess that if that's 10, then that would be my 18, and then 2 would be my 30, and 3 would be my 58, which happens up here. And my dots are represented in a straight line. Looking at these numbers, you know that these numbers are not linear. This guy gives you something that's curved. Again, one last time, the goal of a semi-log plot is to represent logarithmic data as something that looks linear, and C is the guy that does that. F is a periodic function. Oh, we are in 3.1 now. We're talking about periodic functions, which are things that repeat over time. One period of the function is shown in the graph above or below, because again, I stole this from the internet. Hence the name of the series. Using this information, find the value of f of 0. Well, this is periodic, which means it does this and then does it again and then does it back here all over the place. So it looks like from 1 to 5, I have this guy. So every 4 spaces it repeats because, 5 minus 1. So what I'm going to do is I'm going to trace this to the best of my ability, which is pretty bad because I'm not good at tracing, although I'll give myself a little bit of credit there. And I'll scooch this over, boop, like so. And so now what I see is I see f of 0. And f of 0 exists right there at -1. So f of 0 is -1. Thanks for watching. Which of the following angles share a terminal ray with theta equals 300 degrees? All right, let's take a look at what 300 degrees even looks like. Over here you have 0 degrees. Whenever you're talking about rays in precalculus, you deal with all the way to the right first and you count by going counterclockwise. Every 90 degrees, every quadrant is 90. So, starting here would be 90, 180, 270, and so 300 would be something like that going in that direction. Now, every time I spin completely around, a complete circle is the same as 360 degrees. So if I give you 300, I can literally come up with an infinite amount of other measurements that mean the same thing by adding or subtracting 360. So that's what I'm going to do here. I'm going to take my three options and add or subtract 360 and see if I get 300. So for one, if I add 360, right off the bat, I get 300, like the Spartans. And 1 is my option. If I take 660 and I want to try to make it to 300, what I'm going to do is I'm going to subtract 360, and 660 minus 360 is also 300. So 2 is an option as well. I'm going to do the same thing. We're negative here, so I'm going to add 360, and by adding 360, I am at negative 40, so I'm not in the area that I want to be at. If I add 360 again, which means I spin around again, I end up with 320. So close, but only 1 and 2 are going to be correct because only those guys are the same as that. The end. An angle in standard position measures 270 degrees. The terminal ray of the angle intersects a circle centered at the origin with radius 3 at point Z. What are the coordinates of point Z? Time to show off my drawing skills, which are bad. That's a circle. This is a coordinate plane perfectly going through the circle like so. When you measure out an angle, you start out here on the positive x-axis and you work your way around counterclockwise. If we're dealing with degrees, you would be 90 degrees, you would be 180 degrees, you would be 270 degrees, and 0, 360 repeats itself, yada, yada, yada. I need to get to 230. So here's my circle. I'm going to go around counterclockwise from 0 to 90 to 180 to 270 and put a dot right there. Now, the radius of this circle is 3. We're calling that dot Z, and they want to know what Z is. Well, Z is the point on the coordinate plane on the y-axis, 0, -3. So pretty basic problem, pretty simple, and that's all we had to do right there. All right, we are now in section 3.4, and with 3.4, we are given an idea of what the graphs of sine and cosine look like. So when we go into this weird, strange problem that might look like something from 3.3 or 3.2, we now know what cosine looks like. So we are given this angle theta in standard positions shown in the figure. The function g is given by just regular cosine A. For the angle A, which is not shown, A is going to be in between this theta and 3 pi over 2. Okay. So let's graph what cosine kind of looks like. All right, by the way, we only care about up until 3 pi over 2, but let's just graph the first period of cosine, which looks like this. Cosine starts up at 1, okay? At half a pi, it hits 0. At pi, it bottoms out at -1. At 3/2 pi, it hits 0 again and then comes back up and repeats at 2 pi. So let me attempt to draw this out. This never goes well. This never goes well at all. I'm singing you a song. Not bad. All right. So that's what cosine looks like for its first period. And then it repeats. I care about 3 pi over 2, which is this guy right there. All right. So what we know is alpha is going to be larger than theta. It looks to me that theta is somewhere larger than pi over 2. All right, so somewhere. So theta is going to be somewhere in this range, okay, give or take. Okay, so that's theta. Whatever alpha is, alpha's got to be bigger than that, okay? So any of this area right here. Alpha or A, I think I keep calling it A. It might be alpha, I don't know. I'm just thinking of manliness right now, so I keep saying alpha. Basically, what's going to happen is no matter what, since theta appears to be bigger than pi over 2, what's going to happen is alpha, no matter what, is going to be underneath this x-axis, right? I mean, that's what it appears. It's basically saying, I'm going to give you an alpha. I'm going to give you a theta. Theta, at its smallest, is going to be some negative number. Alpha is going to be negative no matter what. So it's safe to say that like alpha could live here, in which case it's bigger than theta. If theta was, alpha could live here, at which case it could be smaller than theta. The question is asking you, like, what's the graph, or what happens if you plug in alpha? What happens if you plug in theta? Is no matter what you plug in alpha, no matter what, you get a smaller value than when you plug in theta? Maybe. Is no matter what, if you plug in alpha, you get the same thing? Maybe. I mean, if theta was this point right here, I could choose an alpha that's the same. If theta was this point here, I could choose an alpha that's larger. And if theta was a point here, I could choose an alpha that's smaller. So this is just a really strange problem where I'm using a very unique situation, again, stolen from the internet, where I need to focus on what the graph of cosine looks like and what that could mean for some random alpha and random theta. So I don't know. I don't like it. This is a stupid problem. But, like and subscribe anyway because you love me and I love you. Which of the following are sinusoidal functions? Now, this is 3.5, and you were probably taught that a sinusoidal function is something in this form. Y equals A, which A is the amplitude, sine times B, which is the frequency. If you haven't learned frequency, you will. Minus C, which is a phase shift, plus D, which is a vertical shift. Okay, so basically, if you can write it out like this, it's a sinusoidal function. Now, if you look at 1, 2 sine theta is just that, where A is 2, and B and C or D, they don't really matter. So 1 is an option. What you don't see is sine being in the denominator. Okay, this will not give you a regular old sinusoidal function that looks like this. So not 2. 3 technically is because cosine is sinusoidal. And basically 4 here is the same thing as 1. It's just you can write this out as 1/2 sine theta. So everything here except for 2 is good to go for sinusoidal functions. All right, we are in 3.6 here in AP Precalculus land, and in 3.6 you are now going to do some manipulation of sinusoidal functions. So a sinusoidal function looks like this. You got y equals a times, this is a sine, so we'll write out sine. When it's cosine, we'll write out cosines. Okay, b times x. And tell you what, we'll leave it like this. This is what this looks like, so we'll leave it like this. We won't write out the whole c and d thing. We'll do that in later problems. What a here stands for is a stands for the amplitude. That's how tall something is. Okay. What b here stands for is b stands for, that's an ugly looking arrow, the frequency. Now the frequency, okay, the frequency is the same exact thing as 2 pi over the period. So if I want to find the period, we can find the period by doing 2 pi over whatever that b is. Okay, so let's do a little bit of math. First things first, before we even graph, the amplitude is the number in front of sine, and in this case, the number in front of sine is 4, so the amplitude is 4. The midline. Now, the midline is basically when you graph this thing, the midline is when you cut it directly in half. When you're not adding or subtracting anything to the whole thing, your midline is the x-axis. Okay, the midline is found by whatever number you add to this whole sinusoidal function. I'm not adding anything. So the midline is nothing. So the midline is the x-axis, so we will say the equation y equals 0. Now what that looks like graphically is, since everything starts out in the middle, since everything is leveled off at the x-axis, my amplitude is also going to be my maximum value and my minimum value. Since I have no vertical shift, my maximum value is going to be 4, and my minimum value is going to be -4. My frequency is the number in front of x. Well, the number in front of x isn't as clear because it's x over 2. But I know I can write this guy as 1/2 x. So B, my frequency is 1/2. Now, I can find my period by doing P equals 2 pi over 1/2. Now, I don't like dividing by a half, so let's multiply the top and the bottom by 2. You're allowed to do that because you know it equals 1. So that's going to cross that out, because a half of 2 is 1. And 2 pi times 2 gives me a period of 4 pi. Now, given all this information, it's time to graph this puppy out. Okay, sine starts out at 0, 0. Since I'm not shifting this thing left or right, and I'm not shifting this thing up or down, it starts still at 0, 0. Everything repeats at 4 pi. Okay, now I don't have 4 pi to take it to. Okay, I only have 2 pi, which means when I hit 2 pi, I go through half of its process. So what's going to happen is the whole thing would look like this. Start here, go up, go down, and repeat. And it would repeat at 4 pi. But since my graph only takes me to 2 pi, I'm cutting it off right there. So this is going to peak out halfway between 0 and 2 pi, which is pi, and it peaks out at 1, 2, 3, 4. And then it goes back to its midline at 2 pi. Now, similarly, going backwards, this thing is going to bottom out at 1, 2, 3, negative 4, and then hit the x-axis again at negative 2 pi. So when I draw that out, which I'm terrible at, it's going to look like this. Remember when I said I'm terrible at it? I wasn't lying. Started off weak, ended off strong. But that's it. Let's get rid of this one. I'm not happy with that one. I'm just going to scooch it over there and make it look slightly better. So there you have it. There's your sine. There's your sine. As you can see, the whole period is seen just on this graph. Amplitude is 4, negative 4 is minimum value. Everything is exactly as it should be. Midline is y equals 0. Yeah. It's our first sinusoidal graph that we ever did here on random SAT, not SAT, AP Precalculus problems that I stole from the internet. I do have random SAT ones. You should check those out too. Like and subscribe. A spring oscillates up and down, and its displacement from the equilibrium position is modeled by the function s of t equals 5 cos pi over 4t, where t is time in seconds. What's the amplitude? The amplitude is just the number attached to cosine, so the answer is 5. Well, thanks for watching. I hope you enjoyed this. Like and subscribe. If the tangent of an angle in a right triangle is 0.75, what can you conclude about the relationship between the lengths of this side? So let's go back to geometry and remind ourselves of SOHCAHTOA. TOA means that the tangent of an angle equals the opposite side over the adjacent side. Now, this has to do with right triangle trigonometry, okay? So it also tells us that the tangent of an angle is 0.75. So let me rewrite this out as 0.75 over 1 equals opposite over adjacent. By writing it out this way, it lets me do a little crisscross applesauce and do a little bit of cross multiplication where I can say 1 times the opposite equals 1 times the opposite, which is just the opposite. That's going to equal 0.75 times the adjacent. Now, by writing it out this way, we can now say a phrase like, I don't know, the opposite side is 0.75 times the adjacent side. The opposite side is 0.75 times the adjacent side. The answer is A. Now, I know there's other ways that we could do this, probably a simpler way, But, this is me just breaking it down and, I don't know, making it simple in my little mind. If sine of g of x equals x and g of sine of x equals x, evaluate g of root 3 over 2. Now, this is 3.9, which is all about inverses. What this guy is saying right here is if sine of g of x and g of sine of x both equal x, that means these are inverses. So what it's asking me to do is to find g of root 3 over 2. So sine x is equal to root 3 over 2 because g of blah, evaluate g of blah, set them equal to each other. So sine of x is going to equal root 3 over 2. And you might be wondering, whoa, buddy, you sure left a lot of space there. I sure did. Because my job is to evaluate this guy, which means solve for x. Okay, so in order to get rid of that sign, I'm going to inverse sine from both sides. Inverse sine from both sides. That crosses out, and you're left with x equals the inverse sine of root 3 over 2. Now, let's remind ourselves what sine means. Sine is the y value of a coordinate. So usually I give you something like the sine of some angle is going to equal root 3 over 2. Well, that's exactly what I'm doing. I'm going to find the angle that gives me root 3 over 2. So sine is positive in the first quadrant for the both of them. So I'm going to deal with first quadrant only stuff. Okay, this doesn't ask me to do with other stuff, so I'm just going to deal with first quadrant only stuff. Okay, sine of x if I'm dealing with unit circle thoughts, or sine of whatever if I'm dealing with unit circle thoughts, is going to be a y value. Okay, so which of these three dots gives me the y value of root 3 over 2? You do. Okay, and so that's the third dot of quadrant 1. Which means this angle is pi over 3. So the inverse sine of root 3 over 2 is basically saying, hey, the sine of what angle is going to give you root 3 over 2? Well, the sine of pi over 3 is going to give you root 3 over 2. So that's what we're going to do. That's how we're going to solve it. Now, there's other problems that might ask you to go a little bit further than this, but we're not quite there yet. Right now, we're just focusing on quadrant 1, so we're going to answer it like that. Solve the equation for theta on the interval 0 to pi. 1/2 equals cos theta. I'm just going to rewrite this like this, and you might be wondering, why? Why all that space, sir? Well, I have to get theta all by itself, which means I have to get rid of cosine. How do you get rid of cosine? You don't divide cosine, you inverse cosine both sides. Inverse cosine both sides. That's why I gave myself that space. Now I can cross this out, and flipping things around, you can now say that theta equals the inverse cosine of 1/2. Now basically what you're doing is you're asking yourself, cosine of what angle gives me 1/2? Well, first things first, cosine is the x value on the unit circle. So where on the unit circle is the x value going to be positive? In these two quadrants right here, quadrants 1 and quadrant 4. Now, where is my x value 1/2? Well, my x value is 1/2 here, which means it's also going to be corresponding here. This is the third dot on the unit circle where x is 1/2. So it would be like 1/2, who cares, root 3 over 2. And this would be 1/2, negative root 3 over 2, but, who cares? Now, most importantly, again, my job is to find out what equation, or better yet, what angle, would give me these numbers. Well, u would be pi over 3, because u would be the third point in my unit circle, and u would be like the negative pi over 3, also known as 5 pi over 3. Those guys fall within the boundaries of 0 and 2 pi, so theta is going to equal pi over 3 and 5 pi over 3. And that's your answer. Verify the identity 1 over sine x cotangent x is the same thing as 1 over cosine x. So I need to make this guy the same as 1 over cosine x. Well, what do I know? Sine is sine, can't do much about it. But what I do know is cotangent is cosine over sine. So let me write that out. Cosine over sine. Oh, look, a sine up here and a sine down there. Let's cross them out. And when I cross them out, I'm left with 1 over cosine x, which is what I want to find. I did it. Verify the identity secant squared x minus cosecant squared x is the same as tangent squared x minus cotangent squared x. What you're doing here is you're basically starting with the left and you're doing some math trickery to see if you can end up with something on the right. So this is what I see here. I see a Pythagorean theorem identity right here and I see a Pythagorean theorem identity right there. Secant squared x is the same exact thing as 1 plus tangent squared x minus cosecant squared x is the same thing as 1 plus cotangent squared x. Oh, how they look so similar to each other. Now, if I take this and distribute the negative, I now have 1 plus tangent squared x minus 1, how about that, minus cotangent squared x. The 1 and the negative 1 cancel each other out, and that leaves me with tangent squared x minus cotangent squared x, which is what I'm trying to find. So did I verify the identity? Sure did. A little check mark says I did it. Rewrite the polar coordinate with a negative magnitude. Now, before I even consider this, let's take a look at what we have. This is a polar coordinate. This is not what we're used to, which is called a regular coordinate. This is not telling us to start at the origin, go right 7, and then up whatever gross number this is. No, this is polar. And the two numbers involved in a polar coordinate, the first number is the magnitude. That's how long we draw a line starting from the 0, 0, which is also called the pole in a polar coordinate system. This is the degrees that we go, just like we've been doing all year long, or all AP Precalculus long, where we would start out counterclockwise from the positive y-axis, x-axis. So, graphing something like this, right? There's my direction, 11 pi over 6 is you spin it all the way around. So it's basically like that. And we have something that's 7 units long. And so my point would live right there. Okay. Now, they want us to do a negative magnitude. Well, a negative magnitude, if I were to take this same exact guy and make this negative 7, what I would do is I would still spin it around to 11 pi over 6, but I would go in the complete opposite direction, that way 7 units. Okay. Now, what I need to do is if I'm going to make this negative 7, if negative 7 has me going in the exact opposite direction, that's a change of 180 degrees, or pi radians. So if I'm going to make this negative 7, then what I need to do is I need to spin this guy around in the exact opposite direction. So I'm going to either add, or in this case, subtract pi. Now, why not add pi? Well, if I add pi, it'll be more than 2 pi, and I want to keep it between 0 and 2 pi. So subtracting regular pi is going to make this look like negative 7. I'll change this pi to 6 pi over 6, and I end up with negative 7, 5 pi over 6. And so the way that I would graph this now, pretending that this guy is no longer there, let's erase you. The way that I would view this graphically is I would go counterclockwise from the positive x-axis to what appears to be 5 pi over 6. But since this is negative 7, I'm going to go in the exact opposite direction and graph the original guy that you see right here. And that's how it's done. Sketch a graph on a rectangular plane to help draw the polar graph for r equals 3 sine theta. Now, whenever I graph a polar graph for sine theta or cos theta, it has a very, very, very specific look as long as it's just sine theta or just cos theta. The number in front of it just makes that picture bigger. That's all it does. So let's kind of draw out what it's asking us to draw out, the trig version of 3 sine theta. Now, I know that 3 sine theta goes up to 3, bottoms out at -3. I know that magic happens at pi, then it repeats itself at 2 pi. It goes through stuff at pi over 2, and 3 pi over 2, yada, yada, yada. So if I were to draw this, it starts out here. At pi over 2, it peaks out at 3. At pi, it hits the x-axis again. At 3 pi over 2, it hits -3, and at 2 pi, it repeats. So, let's just draw a rough draft of what this looks like. Okay, knowing very well that I am not an artist. Those of you who've watched my videos know this. But this will help us kind of figure out what we have. Now, let's draw the dots that we have so far. Okay, this is the polar coordinate 0, 0. Okay, so basically, if I look at it this way, my y-axis is basically my r. Okay, and this is basically my theta. So this is the point 0, 0. This right here is the point 3 pi over 2. So I go to pi over 2, I draw a dot at 1, 2, 3, right there. Okay, at pi, I have 0 again. So if I were to go over to pi, I put a dot at 0 again. So it looks like, I just kind of hit that again. At 3 pi over 2, which is u, I'm at -3. So 3 pi over 2, I'm at regular 1, 2, 3, but spin it in the opposite direction, and I'm covering that dot again. So right now, and then of course 2 pi is the same as 0. That's where it repeats. So, 2 pi is 0, the same thing. There's a dot. So really, I only have 2 dots. So drawing this graph, I'm kind of out of luck. So let's kind of find some in-between areas. Okay, so if I were to put a little mark here, 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 and here, that kind of gives me those in-between areas. Like at, pi over 4 and 3 pi over 4 and 5 pi over 4 and 7 pi over 4. I could put more dots there. It looks like at pi over 4, I'm at like the 2-ish range. So even though I can't see pi over 4, I'll write it out. At pi over 4, I'm at the 2-ish range, give or take. At 3 pi over 4, I'm also at the 2-ish range because this is sinusoidal, and whatever it does over here, it kind of has symmetry. So I'm at the 2-ish range there. At 5 pi over 4, which would be u, at 5 pi over 4, I'm at like the -2-ish range, which means I'd go here, but in the opposite direction, which means that dot just repeats itself. So if this is going to be 7 pi over 4, and if I were to go 7 pi over 4, which seems to be in the -2-ish range, the same exact thing happens. So what's happening here is as I start out at, so I kind of see what's happening. It's circling around. So as I start at 0, 0, and as theta increases, I get further away from the 0, 0, from the pole, until I hit 3, and then I get closer to the pole as I approach pi. So starting out at 0, 0 and spinning around this way, I can kind of put like these dots around here, and that kind of gives me an idea. Okay, and again, as I'm going from 0 to pi, I slowly go from 3 and then back to 0. So from 0 to pi, I go from 3 and back to 0. Now, from pi to 2 pi, I do the same thing, but negative. So as I go from pi to 2 pi, I go like this circle, but in the negative area. So when all is said and done, what I do is I loop around and make a circle twice. But you don't see it twice. All you see is just a nice, perfectly round circle. So whenever we have 3 sine theta, 4 cos theta, 8 sine theta, negative 20 sine theta, whatever, if it's sine theta with no frequency in front of it, we're going to have a circle. And that size of that circle is going to be based on a 3. So this goes out to 3 and it makes a sine. Cosine is going to be over here. Negative cosine is going to be over here. And negative sine is going to be over there. So a lot of problems that you would see on the AP Precalculus exam might be like, look at this guy, pick the picture that works. And you could make a trig graph and do the long way, or you could just memorize the fact that if it gives you a circle, if it gives you something that looks like this, or something that looks like this, or something that looks different, you're going to pick the circle because sine theta or cos theta, when drawn on a rectangle, on a polar plane, gets you a circle. Isn't that neat? Plot the point in the complex plane. I'm giving you a complex polar coordinate given to you in the form 3 cos stuff plus I sine stuff. Sometimes you're used to seeing it as r cos theta plus I r sine theta, but this is another way of writing it out. Well, this is how you graph these guys. 3 is your magnitude. That's the distance from 0, 0 to the point that you're going to draw out. There's my theta, and we treat that theta the way we've always treated theta. You start at the positive x-axis and you go your way counterclockwise. Now we are going to 7 pi over 6, and our magnitude is 3. So all we do is just draw a dot at what? 1, 2, 3 at 7 pi over 6. So that's it.